Welcome, ladies and gentlemen, to a lecture on solving problems using conservation of momentum. Today, what I'm going to do is I'm just going to solve 3 example problems just to show conservation of momentum in use, just to model it for you guys. Okay? So the first problem, you're playing pool. You hit the cue ball so that it rolls over and hits another ball straight on, and that ball rolls into the pocket. What is the velocity of each ball after the collision? So if we're looking down at the pool table here, this might look like one ball goes over, hits another ball, and what we're assuming is straight on. So the center of masses of each ball are lined up with the velocity vector here, okay? So they strike center on like that, which means that this ball is going to roll off in this direction too. So everything's in a straight line. So if I was looking at it instead of from the top like that from the side, I just have one ball rolling over and hitting another ball, okay? This one has M1, this one has M2, and this one has V initial, okay? Okay, so we're going to solve this problem with conservation of momentum. Which is Pi equals Pf. All right? And again, remember we're finding V1 final and V2 final. Okay? So with billiard balls, we're talking about an elastic collision, right? The two balls roll over, they hit each other, they're both very hard, and we have an elastic collision. Additionally, with the rolling on the tabletop, we can also assume that there are no external forces. Now, is there probably a tiny force of friction on the ball as it rolls? Yeah, sure. But it's so small that we can really consider it negligible, and we're still okay to use conservation of momentum. Okay? So we're using conservation of momentum for an elastic collision. Right? And that means that Ki equals Kf. So let's write both of those. Initially, we have M1 Vi, right? That equals M1 V1 final plus M2 V2 final. That's our conservation of momentum, right? All of the momentum of the system is in the first ball at the beginning because the second ball has a velocity of 0, right? It's just sitting there. And then at the end, we have these two, and we don't know V1 and Vf, so we're just going to write the individual momentum of each ball, okay? And then for kinetic energy, we have the same thing. 1/2 M1 Vi now squared. That's all the kinetic energy in the beginning, right? It's the only ball that's moving. And then we don't know V1 final and V2 final, so we'll just write, in general, the total kinetic energy of the system at the end is whatever the kinetic energy of the two balls is after the collision. Okay? So we can rearrange this second equation, this equation of the kinetic energy, so that we have all the M1s on one side and we have the M2 on the other side. So then we have M2 V2 final squared equals M1 Vi squared minus M1 V1F squared. Okay? That's equal to M1 times this difference, Vi squared, minus not just F, V1F squared. Okay? And that's equal to M1. And then to get this, I'm just going to show you guys what this product is, and you can multiply out the terms and see that it'll return this little piece right here, okay? So if I have the product of Vi plus V1F times the product, or times Vi minus V1F. Okay? If I multiply those together, it'll come out to Vi squared minus V1F squared. Okay? Then I can take the momentum equation up here, and I can do the same thing. I'm going to have all the M2s on one side. Okay? So M2 V2F equals M1 Vi minus M1 V1F, okay? And that's equal to M1 Vi minus, again, not just VF, V1F, okay? And now you can see why I did this funky thing up here with the energy equation, right? Now it's starting to make sense. So now if I look at these equations, I notice that I have something interesting. If I say take the left sides here and divide the energy equation by the momentum one, right? So if I do M2 V2F squared, everything on the left side of this equation, divided by everything on the left side of this equation below, V2F, that equals V2F, right? This one cancels the square, and the two M2s cancel, okay? That's good because V2F is one of the things that we're trying to find, right? But then I have to do the same thing for the right sides. So if I take this one, right, it has to be on top, right, because I had the top here on the left. So this one's on top, M1 Vi plus V1F times Vi minus V1F, okay, over, and then I'm going to take the right side from this equation and put it on the bottom just like I did for the left side, okay, M1 Vi minus V1F on the bottom. And now, like I said, you can see why I was doing this funny stuff with the energy equation, because this thing in the parentheses is the same exact term as this thing, so they cancel. The M1s cancel, and I get that V2F equals Vi plus V1F. Okay? So then I can go back to this equation, the bottom guy here, and I can plug in V2F, okay? And then I have M2 Vi plus V1F equals M1 Vi minus V1F, okay? I can expand my terms here, so I have M2 Vi plus M2 V1F equals M1 Vi minus M1 V1F. Okay, if I do some algebra here, then I get V1F times M1 plus M2 equals Vi times M1 minus M2. And that tells me that V1F equals Vi times M1 minus M2 divided by M1 plus M2. And now I have one of the things I was looking for, right? I have V1F, and this one is in terms only of things I know, the initial velocity and the mass of each ball. So this is going to be equals M1 minus M2, M1 plus M2, Vi. That's one of our answers. And we can see just immediately that the units work, right? Kilograms over kilograms here, and then meters per second. So units work. Okay, so I have this expression for V2F. I have a final expression here for V1F. The problem with my V2F expression is that it has this V1F in it, right, which isn't a known. But I have V1F in terms of only things that I know. So all I need to do is make a substitution to get V2F, okay? V2F equals Vi plus all of this stuff. Vi times M1 minus M2. Oh, that should be a minus. Over M1 plus M2. Okay? And then we simplify. We're not cave people here. We don't leave it in this barbaric form. We simplify. And the way I'm going to simplify is I write Vi, and then Vi times 1 is still just Vi, right? So what if I just wrote M1 plus M2 over M1 plus M2? Well, that works, right? That's just 1. And then I have M1 minus M2 over M1 plus M2, okay? And then that means I can pull out this Vi, and I can add these two fractions together because they have the same denominator, right? So the stuff on top just adds together. What does that leave me with? It leaves me with a 2M1, and then the plus M2 minus M2, well, that's just 0, right? Over M1 plus M2. And now we have V2F in a much nicer fashion, right? So now we have these two expressions, and these were really just for two balls in an elastic collision, right? But now, it's two balls in elastic collision, assuming that this ball, M2, had no velocity at the beginning, right? Because we put those zeros in. So it's not totally general, but it's for one ball bumping into another ball that's at rest. Now, in the case of billiard balls, the reason that pool works so nicely is that all the balls have the same mass, right? So in the case where M1 equals M2, so if M1 equals M2, let's get this guy out of here. We don't care about him. Then V1 final equals 0, right? Because this numerator, this M1 minus M2, well, if M1 equals M2, we could just write that as M1 minus M1. That's 0, right? So V1 final equals 0. If I hit the cue ball and it hits another ball straight on, the cue ball just stops, okay? But then also if M1 equals to M2, then V2F, you can see I have a 2M1 on top, but if M1 equals M2, then I would have M1 plus M1 on the bottom, and I'd have a 2M1. So V2F equals VI, okay? So when I hit a ball dead straight on the pool table, what happens? The cue ball rolls over with some speed, VI. It bumps into the other ball. It stops, and then the other ball leaves with the initial velocity that the cue ball had, okay? The same exact speed that the cue ball had. And this is due to the two balls having the same mass, okay? So a lot of people think that when you play pool, you need to put backspin on the ball to make it stop when it hits the other ball. This isn't true, okay? All you actually have to do is make sure that they're aligned so that those center of masses hit each other nice and square, okay? The cue ball won't stop if it comes in and hits like this, but the velocity is like this, okay? So that the velocity of the cue ball doesn't have the vector of velocity. It's not able to be drawn right through the two center of masses, okay? So if V is like this, cue ball stops, other ball goes off, just like we just solved. If V is like this, then they both shoot off in different directions, okay? So all I actually have to do in pool to make the cue ball just stop when it hits the other ball is just hit it straight on the other ball, okay? And again, this also doesn't depend on VI, okay? the cue ball will stop when it hits the other ball, no matter how hard I hit it. Assuming I'm not like the Incredible Hulk and the balls don't explode when they hit each other or something like that. But no matter how hard I hit it, the cue ball will just stop if I hit the other ball dead on like this, so that the velocity vector goes through the center of mass of each ball. Okay, and I make it a one-dimensional problem like this. Now, if I had two balls and they were different masses, I would end up with something entirely different, right? So what if M1 is very, very small, okay? And M2 is very, very, well, let's make it comparative here. It's very, very small. We'll just write it like that. Much, much smaller than M2, okay? So if M1 is really tiny, this V1F, okay, is going to be basically equal to minus VI, right? If M1 is really, really tiny compared to M2, then this fraction right here, if it's so small that, say, when we consider the mass of both of them added together, it's really just M2, okay? So like if it was a bowling ball and a ping pong ball, right? A bowling ball plus the mass of a ping pong ball is really just basically the mass of the bowling ball, right? Or like a train and a baseball, like I used in the last lecture. An entire train, the mass of an entire train plus the mass of a baseball is just the mass of an entire train, right? So if I have that approximation, then this looks like minus M2 over M2 is what this fraction looks like. And what that means is this is minus 1 times VI, and I just get minus VI. Okay? So when I do that, I have the really big object sitting still, and I throw the little tiny object at it. What happens? Well, it just bounces right off, right? And essentially what happens is that it has the same velocity that it had going in, but now coming back out, okay? And you can imagine if you think about tossing a ping pong ball off of a bowling ball, that's exactly what would happen, right? It would be coming straight in, it would hit the bowling ball does nothing, ping pong ball flies out with whatever speed it hit the bowling ball with, okay? Now I said bowling ball does nothing, but would that hold true in our equation? If we look at V2F, okay, we have the bowling ball with the great big mass. Now M1 is really, really tiny compared to M2, and so I essentially have 0 over M2 in this thing, right? It's so tiny compared to M2 that this 2M1 is still basically nothing compared to M2 times VI. And so now I have a 0 velocity. So, yes, bowling ball does nothing. V2 final is nothing. Okay? So one last case to consider on this. What if M1 is way bigger than M2? Okay? So now it's the train moving and the baseball just sitting on the tracks. Okay? If that's the case, if M1 is way bigger, then this V1 final is essentially just VI, right? Because this thing here, just like when it was M1 was the super tiny one, it was minus M2 over M2. Now when M1 is the really big one and M2 is inconsequential compared to M1, this is just 1 and our thing comes out with VI, okay? So if the train hits a baseball on the tracks, what happens to the train's velocity? Well, essentially nothing, okay? The amount of change in the train's velocity has this kind of mass sum proportionality, and that thing is so unchanged by adding in the mass of the baseball that the train's velocity is essentially unchanged, okay? The train's momentum is unchanged, and so its velocity is unchanged. And what happens to the baseball? Well, now M1 is way, way bigger than M2. So my M2 I can ignore, and I have 2M1 over M1. And what I end up with is 2 VI. Okay? So what happens to the baseball when it gets hit by the train? Well, it goes flying out really, really fast. Okay? Now, you can think about this. An interesting way to think about this is, what if I, instead of looking at it from the outside, I just looked at it from a coordinate system that's attached to the train. So my coordinate system moves with the train. If that was the case, and my coordinate system was fixed to the train, what it would look like in that coordinate system, if I couldn't see any background or anything, there's just a floating train and a floating baseball, is that the baseball is moving in the coordinate system, right? The coordinate system is stuck to the train, and the baseball looks like it's flying in and hitting the train in that coordinate system. If that's the case, then I'm back to the ping pong ball bouncing off the bowling ball, right? And so what happened? It was flying in, and then it flew out with the same velocity that it flew in, right? But the other direction. So the change in velocity of the ping pong ball hitting the bowling ball was 2 times the velocity that it came in with, right? Because it went from plus to minus. So it's 2 times VI is the change in velocity. So when I go back to this, the baseball sitting still and the train hitting it, if my coordinate system was attached to the train, it would look like the baseball flying in and hitting it, and the change in velocity would be 2 times the velocity that flew in, okay? When I go back out and my coordinate system isn't attached to either of them, I'm just looking at it from the outside, the change in velocity of the baseball is still exactly the same. It's 2 VI. But now the baseball was sitting still, and when the train hits it, the baseball is launched off the front of the train, okay? Okay, let's look at another example here. You are playing football and have the ball. You are running straight up the field with the ball. Another player is running straight down the field at you. He tackles you, hanging on so that the two of you are now stuck together. What velocity do the two of you have after the collision? Okay, so we have you here with the football running real fast, and some guy running at you also real fast to tackle you, okay? Let's say we know his speed is V2, your speed is V1, okay? Your mass is M1, his mass is M2. And let's give a coordinate system like this, okay? Then we also know that the two of you are now stuck together, okay? So when he tackles you, he wraps his arms around you so the two of you are stuck together, okay? So we know that we have an inelastic collision. So Ki not equal Kf, okay? Okay, so we're going to use conservation of momentum. And that means that Pi equals Pf, right? This one's also going to be one-dimensional. It says that you're running straight up the field and the other player's running straight down the field. So the problem setup conveniently makes it one-dimensional, all right? And so in our coordinate system, we have M1, V1 in the positive x direction, and we have in the negative x direction M2, V2. That's our initial momentum for the system of these two players, okay? That's equal to, now afterward, the two players become one object, right? They're stuck together. So they're one object that has a total mass M1 plus M2, all right? So we're assuming that he tackles you and wraps his arms around you so that you guys become one mass, but he doesn't hit you so hard that like an arm flies off or something like that, right? You still have the same mass, he still has the same mass, so the new object must have just the sum of your masses, okay? And then this is going to equal V final. This new object has some V final, okay? Now, this one, it's really, really easy, right? This one's basically already solved. We wrote one equation. We only have one thing that we don't know, V final, okay? So V final equals M1 V1 minus M2 V2 over the sum of the masses, M1 plus M2. Okay? You can see on the top we have kilograms times meters per second, and on the bottom we have just kilograms, so we have meters per second for units, okay? So in the case where V1 equals V2, you guys are equally fast, which direction does VF end up in? If that's the case, what's going to make the difference is these masses, right? M1 and M2. So if that's the case, then we go in the direction of the bigger guy, okay? Then VF goes with the big guy. Okay? So if we're running the same speed and we bang into each other, if I'm bigger than him, our velocity at the end is going to be going in my direction. Okay? So what does that mean? Well, that means that he's going to have a much bigger change in velocity than I am, right? His delta P for the other guy is going to be really big because it's going to go from M2 V2 equals, right? So this one was minus to plus M2 VF when we're one object here at the end, right? When in this case. So his delta P is equal to, let me get this stuff out of the way, is equal to M2 V2 plus M2 VF. That's the delta P for the guy that tackled me if I'm bigger, right? And then my delta P is going to be, remember that I was going that direction in the beginning, so it's going to be M1 VF minus M1 V1, right? So my delta P is going to be much, much smaller, right? His are going to add together. He's going to have a really big delta P. His momentum changes a lot because he changes directions, right? So what does this mean in real world terms? It means it sucks to be that guy, right? It sucks to be the guy whose momentum changes a lot. So then if we flipped it, if the guy tackling is the big guy and they're going the same speed, then you can see what happens is our V final is going to be negative, right? We're going to be going in the direction he was going. And then if that's the case, what does it mean? Well, it means it sucks for you because you're the one with the great big delta P in that case. All right? So then what if M1 equals M2? Well, then VF goes with the fast guy, right? Well, now it's whoever's faster, okay? So if he's running twice as fast as you when you guys collide, then your final velocity is going to go with him, right? If you're running faster than him and you guys are the same size, final velocity is going to go with you, okay? And you can see we have this give and take, all right? These were the extremes. What if you're the same mass, or what if you're the same velocity? But what we ultimately have on top here is this relationship where we're comparing the momentum before the collision of one guy with the momentum before the collision of the other guy, right? And it's a difference. And you can see the sign of VF is going to be the same sign as whichever one of these is bigger. So if M1 V1 is bigger, then VF is positive. It goes in the direction of the guy with the ball in this case, okay? If M2 V2 is bigger, then it goes this other way, okay? And the thing is, they're proportional. So if you're twice the size of the other guy, but you're running half as fast, then VF ends up being 0, right? So if you have 2 M1 V1, or let's take the ones off. Okay, you're twice the mass, but you're half as fast, okay? Minus, he's half the mass, but he's twice as fast. Then what happens is, that equals 0, right? So then you guys just stop when you're one piece, okay? But the momentum is proportional to both the mass or the velocity. So to kind of quote-unquote win, to have it go in your direction at the end, you either have to be bigger with your speed close to his, or faster with your mass close to his, or so much faster that even if you're much tinier, the total momentum, your momentum is bigger than his, or slower but so much bigger than him that again your momentum is bigger than his. Okay? So this piece up here in top, this thing, this is what's going to decide the direction of V final when these two objects hit and stick together, okay? Whichever side has the bigger momentum before the collision, that's the way that V final is going to be going after the collision. Okay, let's look at this one last example for the day. Two cars collide at an intersection and stick together. Before the collision, one car is traveling with a constant velocity north, and the other car is traveling with a constant velocity east. What is their final velocity after the collision? So in this case, we have a car here going east with V1. We'll call this one M1. We have a car here going north with V2. We'll call this one M2. Okay? And then they collide, and we have some new conglomerate object with some V final. Okay? And the mass, M1 plus M2. Okay, this stick together always tells us that we have one big thing with the mass equal to the sum of the two little things, right? That's what stick together always means for us. So in this system, because one car is traveling north, one car is traveling east, it makes a lot of sense to just use a coordinate system that looks like this, okay? And now remember that our vector equation is going to have components because this isn't a one-dimensional problem now. With the velocities pointed in these two different directions like this, this cannot possibly be a one-dimensional problem. Okay, so we're going to use conservation of momentum. And this is an inelastic collision, so we're not going to use conserved kinetic energy. We're just going to use conservation of momentum, which says Pi equals Pf. And then this time, again, we have to break it into components, okay? So let's consider the x-hat direction first. Initially, in the x-hat direction, we just have m1, v1, right? Because this thing points right in my x-hat direction, this guy up here. And then that's equal to, at the end, we have the two masses stuck together, so we have the mass of this big conglomerate object now, times v final, my speed at the end. And then if I look up at this picture, I've defined theta to be the angle above the x-axis, okay? And if I draw my little triangle here, I have VF, and then this one is going to be VFX. This is going to be VFY, and VFX equals VF cos theta, VFY equals VF sine theta, right? Just using SOHCAHTOA on this triangle. So this is going to be M1 V1 equals this conglomerate mass M1 plus M2 times VF cos theta. Then let's write conservation of momentum in the y-hat direction. M2 V2 equals M1 plus M2 VF sine theta. Okay? And then the problem, remember, wanted me to find the speed after the collision. Okay? So how am I going to do that? For me, the way that makes sense to me to do this is I'm going to square both of these equations. Okay? Let's put a line here to really make it clear these are separate. But now I'm going to square this first one. M1 squared V1 squared equals M1 plus M2 squared VF squared cos squared theta. And then the same one for this one, M2 squared V2 squared equals M1 plus M2 squared VF squared sine squared theta. Okay? I just squared both sides of both equations. All right? And then what I'm going to do is add them together. So I have m1 squared v1 squared plus m2 squared v2 squared. All right? And that equals, you can see if I add these two terms together, there's a bunch of stuff that they share, right? They both have an m1 plus m2 squared out in front, right? If I'm adding these two right sides. They both have a vf squared. And then the two terms added together would be a cos squared theta from the first one plus a sine squared theta from the second one. Okay? And then what I do with this is this thing in the parentheses here, this is actually has a trig identity. Cos squared plus sine squared equals 1. Okay? That's just a trig identity. And that allows me to get this nasty angle out of my equation because all I'm actually trying to find is speed, right? And so then that makes this right side equal m1 plus m2, that whole quantity squared, vf squared. So then I have vf squared equals m1 squared v1 squared plus m2 squared v2 squared over m1 plus m2, that whole quantity squared, right? And that means that vf equals m1 squared v1 squared plus m2 squared v2 squared over, that all in a root, right, over m1 plus m2. Okay? Now, we see that the units work, okay? I have kilograms squared, meters squared per second squared up top. I take the square root, that's a kilogram meter per second. I divide by kilograms, I end up with meters per second, okay? We can also see that V final increases as V1 increases, right? I just look at my equation. If I make V1 bigger and keep everything else the same, V final gets bigger, okay? We can also see that V final gets bigger as V2 gets bigger, okay? Again, I just look at my equation. If I make V2 bigger, V final will get bigger. Then I think about each in the real world. In the real world, would it make sense that I would have a bigger final velocity if either of the two cars was going any faster? That does make sense, okay? All right, so now why does it end up looking like this? Well, in this case, I was able to write my coordinate system so that the initial momentum of each vehicle was the initial momentum in one coordinate direction, right? So when I wrote my conservation of momentum, I was able to write for initial, P initial over here, either M1 V1 for the X direction or M2 V2 for the Y direction, okay? So there was no kind of mixing of the momenta in the initial. So then the V final, what I get is this thing here that looks kind of like a Pythagorean theorem addition of the momenta, right? Which makes sense, but now, remember, kinetic energy wasn't conserved, so now I end up dividing it by this mass of the new object to get V final, okay? So when the equation was written with this M1 plus M2 on the other side, what I got was this M1 plus M2 V final. That's just the momentum after the collision, right? It's just the mass times the velocity after the collision is equal to this kind of Pythagorean sum type of thing of the momenta before. And the reason that it looks like this is because each of the vehicles was pointed in one of my coordinate directions to start, okay? If they had been pointed a little off so that I couldn't, so that the PI in each coordinate direction wasn't just one of the vehicles, I wouldn't have this form at the end, right? But they were, so I have this nice kind of Pythagorean looking equation where my final momentum is something kind of analogous to like a Pythagorean sum of my initial momenta, okay? So those were some examples for solving problems using conservation of momentum. We'll look at some more examples in the next lecture. And again, the homework will give you ample opportunity to practice conservation of momentum so that you get a really nice grasp on using this tool to solve for quantities in physical systems.